Yeah, okay, no, hopefully the coffee helped a little bit. We started before the break with a very dissatisfying result that the thing is not moving, but actually by definition it's correct that the thing is not moving, right? That the position stayed the same. And I already in the audience heard somebody say the magic word. So what is the magic word here? How can we solve this? What did we calculate? Again, what did we calculate? Now we calculate the position, yeah. But previously, before that, from the equation of motion, we determined the accelerations. What are we going to do with them? Throw them away? No, we have to do something with them, right? So that is the whole solution to our problem. Yes, the speed is 0 at this initial time, meaning we're not moving in that sense, but our speed is changing. That is what Newton tells us. Newton tells us if you apply a force, then the speed will change. And if you start with a 0 speed, you're not moving, but your speed can change due to these forces. The gist, the essence of the Newtonian equation. So let's do that. We calculated what the accelerations are at the initial configuration. So, of course, I knew the answer. Yeah, I need a little bit help here. If I double dot in the initial configuration, this was 6 point help 49 or sorry? 6.29. Thank you. Oh yeah, that cool. So that is the thing which I initially had already with a figure, right? Delete. Delete. Nou, kom op. Yeah, the 1 and 2. Very good. 1, 1, 1, 2, 2, 2. Yeah, this was a 0. This was minus 20 point whatever, 9 or something. This was 10.51 from memory. And what was phi double dot 2?
6.98.
Really? 6.98 plus. Yeah. Okay. And now again on this set of variables, right? We can apply this Euler step. So we start with a velocity of 0 and then with a time increment of 0.1. we see that the velocity changes. And what does it become? Well, it becomes 0.629. Well, let's make a 3 out of that, right? 6.3. This remains 0. Well, that's how it is. This becomes minus 2.1. This is 1.1, right? This is, it's all approximation 0, and it is 0.7. Okay, so the outcome is we still are in the same position with the mechanism, but now it has picked up speed. So let's do again. We take a next step. We go to this one, 0.2. So again an increment of 1 over 10. And now we see that these coordinates will change because we have finite speeds here. So then the coordinates become 0.063. This remains the same. This becomes what is it? Minus 1.55, right? That's a plus, sorry. This becomes 0.11. This remains the same. And this increases a little bit with 1.64, something like that. So yeah, we now found a position which is a little bit changed from the previous one. And how do we find the new speeds? Well, then we have to calculate the new accelerations here, which I don't have. So we have to put in our state vector this position and this speed. And then we have to recalculate the acceleration, and you will see, well, the position didn't change, but we now have speeds. So this will change a little bit. There will be a little difference in these numbers. And therefore, this will increase a little bit different, etc., etc., etc. I'm not going to do that here by hand, of course. And then slowly the thing will pick up. So, and I made a small animation of the first few steps of this. And where is it? Lecture 2. Yeah, here. Well, here you see, no, why is it not working? I have to open it in a browser or whatever. Well, initially, these are the, it's an animated GIF, it should run, help. If I do it in the browser, then probably it will run, right? Help, this one. Yeah. So this is what happens. So let's do that again, right? Oh, oh, it doesn't matter. Okay, so we see the thing moving in the way we expect. Body 1 is falling in that direction, body 2 is in the other direction. But what is most remarkable here, it snaps. Things are falling apart. How can that be? Constraint. Well, we applied constraints, right? Otherwise we couldn't calculate the acceleration. I saw one hand there.
There's an error build up due to the integration.
Yeah. Still, if I do it with a smaller step, still things will fly apart. Other hands.
Well, it's basically the same thing, but it either overestimates or underestimates the solution.
Yeah.
There are the methods that can sort of help you get rid of the error, or at least make it smaller.
Yeah, which methods? Should we just decrease the numerical integration or use another numerical integration scheme, and would that solve our problem? No, okay, stop. That's enough. You would think, okay, I take a smaller time step, or I use a fancy Runge-Kutta 645 scheme, which I discovered in MATLAB. Things will still fall apart. And the essence in this case is that, yes, we enforce the constraints, but on which level do we enforce the constraints? We solve the equations of motion, which are expressed in accelerations. So in essence, we apply the constraints on the level of the accelerations. Whereas we like to apply them on the level of coordinates, because we don't want things to fall apart. So we have to find a way, if we have some speeds and if we have some new coordinates, to sort of get them in order, reassemble, get rid of all those small errors, because those small errors will grow and they will build up. That is the topic of one of the last lectures in this first quarter of the course, that we will find a nice numerical way to solve that. For now, we just have this build-up of errors. Okay, back to the notes. So what did we do? We had the accelerations. We now have a scheme to find the subsequent position, so we can find the function as the whole thing as a function of time. All very nice. Now, while doing your homework, some of you may have discovered that actually you are doing too much work. And that's never good. That's never good to do too much work. I also don't like too much work. So let me, in short, rephrase. If we set up these equations of motion, right? We have this big matrix. We have x double dot 1, y double dot 1, phi double dot 1, etc. Oh, I better can write it out. 2, yeah. And then we have these forces, VA, HB, and VB. And then we have a right-hand side. For now, I don't find that so interesting. I find this matrix interesting, and especially the structure. And this was all M1, M1, I1, M2, M2, I2. There's an diagonal, and everything is 0 here. If I write nothing, it's 0. Well, 0 is nothing, nothing is 0. Then this block was also all zeros. Now I want to write down in detail what we have here. Minus 1, 0, 1, 0. 0, 1, minus 1, 0, 1. And then a shorthand notation, L over 2. I assume that all the lengths are identical of the two bodies. And this is sine phi 1. And this is L over 2 cosine phi 1. This is minus L over 2 sine phi 2. And this is L over 2 cosine phi 2. Lost the connection? Oh, here? How? Why? There's something spooky in this room. I made a call about the wireless not working properly here, but apparently that is not resolved. Yeah. Go to this guy. Scan. The connection again. So this was the second time it happened now, right? We have to keep track of this. Okay, go back up, go back here. Where was I? Yeah, okay, so these are the first 3 rows. They all come from our equations of motion or from our free body diagrams. And then the following 3 rows are 0, 0, minus 1, 0, 0, 0, 0, minus 1. And then we have L over 2. Oh no, zeros of course here first. 2 zeros. And this is L over 2 sine phi 2. And I think over the minus even. And this is L over 2 cosine 2. Okay, now I have to fill in this last part. And that was minus 1, 0, 1, 0. 0, minus 1, 0, 1. Yeah. Then minus L over 2 sine 1. L over 2 cosine 1 minus L over 2 sine 1 L over 2 cosine 1 0 0 minus 1 0 0 0 0 minus 1 0 0 0. No, that's the last is not a 0 of course. That's the minus L over 2 sine 2 and that's the L over 2 cosine 2. Now, why do I go into the trouble to write this down? Clearly, if you look at these matrices, they have a relation, right? I mean, all the entries I see here I see here. So, and we already wrote down, like, if the matrix has this structure, capital M, and this was A, and this was B, and this was 0, then it must be that A transpose is B, right? Okay, that's nice. But it means that either part you can just omit in your derivation. I mean, if you have one part, then you can forget about the other one. So we have to think, where did we get all these entries from? So first, these are the 6 equations of motion, right? So these are just from our Newton-Euler stuff, or in other words, these come from our free body diagrams, right? All these equations. We agree on that? Yeah. So all these entries come from our drawing our free body diagrams, right? By putting in forces and horizontal minus and plus and torques and whatever, and that gave all these entries times these forces. Now these 4 equations, these are the constraint equations. And these entries came from differentiating them twice. On the right hand side we also have terms, but this Jacobian type of thing came from the differentiation of those constraint equations. Now a smart mouse in the audience would think, hey, bugger all, there must be a relation between doing free body diagrams and writing constraint equations, right? I mean, if we end up with the same result, or in other words, I could put my hand on this. Yeah, it doesn't work if I do this. You don't see that. But so I put my hand on this. You cannot see this. It's not there. Then I can easily derive the whole set of equations by just taking the constraint equation, differentiating it twice, and flip this matrix and put it there. But that opens a huge opportunity. And your opportunity is, you do not need to if you follow that scheme, what do you do? What's not needed to do?
Differentiate.
No, we're going to do this. We differentiate this, we write this down, but then we flip it and just put it here. So what did we do then not do? Make free body diagrams. Wow. That's heaven. I mean, tell it to Heike. It's all very nice, but free body diagrams, forget it, we don't need it. Superfluous, eh? You don't need to make the free body diagrams. And that's actually a very, well, yeah, you could argue, yeah, but then on the right hand side, well, these are all forces at the center of mass and they have nothing to do with cutting the bodies and doing it's just putting in the forces there. So that is a very attractive scheme, because I noticed that you are lousy at making free body diagrams. So in this course you can just skip it. You say, oh, we don't do that. And that's actually the whole topic of today, the systematic approach. So there is a way, a systematic way, by which you can just take your system, define your constraints, and come up with your constraints equation of motion without drawing free body diagrams. It's a bit in the spirit of Lagrange, which we will meet later on in this course. Okay. Systematic approach. Systematic approach. How does that go? The concept we need here, we need a new concept, and that is power of a force. Power of a force. Again? Oh, go to the service point, complain. What is this? I mean, it's not me. So let's see the what was the order of things. First, the screen died. Was it the screen died right here? This screen died, correct? Freezes or died? Freezes, yeah. Because my order of things was, you say "oh" about the screen, and then a few seconds later, my tablet drops out here. So there is a sort of order of things. And I expect it has to do with this projection stuff, but I don't know. Okay. Luckily, I can fix it. So this is thrice, right? Third time. Processing, don't come on. Oh, back again. This goes away. Connect. Yeah, here we go. Okay. Here we are again. Okay. So power over force. So what is power over force? So in our case, we define the power as capital P. We have forces which have, in principle you would say it's the force times the velocity, right? But our forces are like vectors. So you have to do the sum of those components, component-wise. There is a way to write it with vectors. Then you say F transpose times x dot. Then you also get the same thing. And actually, I have a notation which goes like this, and I borrowed it from a smart guy. I borrowed it from Einstein. Yeah. So this is the Einstein summation convention. So it's not a meeting where we meet where all the Einsteins meet each other, which would be cool too. But the Einstein summation convention is that if there's a repeated index, you sum over it. So this repetition of I implies the summation. It's just that you don't want to write all the time sum. And I should have written I is whatever to whatever, and you don't want to do that. Okay, so that is the definition of a force, of a power over force. Now, actually, my thing is I also want to talk about virtual power. So what is virtual power? Power you not really have. Like you want to be Donald Trump, but you're not. That's virtual power, right? No, what's... No. The Einstein summation convention just tells you if you see a repeated index, then we apply summation. We assume summation. Oh, a dot, yeah, because power. Ah, thank you, yeah. That was about its power. Thank you. Good point. So virtual power. What is virtual power? Well, you could say virtual power is this. PV is the real velocity, but some virtual speed. So you have some arbitrary speed distribution. I mean, if you take a picture of a mechanism, that's the mechanism, and then you can draw arrows like, oh, these are the speeds in the mechanism, or you draw different arrows. That's the concept of virtual velocities. So virtual speed is defined as the actual forces working on the system times the virtual velocities. And virtual velocities are not things which should be small, or it's just hypothetical velocity distribution. For instance, for our mechanism, for our system, we could say, well, x dot is 1 and the rest is all 0. That's a virtual velocity field. Or x dot is 3 and y dot is -2, and you can think of anything. That's virtual. Now, I use here a sub-index to write vertical. That's not what you're used to. You are used to some Greek strange character, right? I don't know why we do that. Maybe we have to pay the Greeks for that. That's the whole scheme. I don't know. Anyway, we use this, delta, this strange thing. This means virtual. But virtual has nothing to do with differentiation. Nothing. They are dissect. Male, female, totally different. Nothing to do with each other. Yeah? Okay. So that is virtual power, and then we say the real forces times virtual velocities. And I really hope that now in your head you have, this curly delta has nothing to do with differentiation. It's just a hypothetical velocity field. In the same way, you could also define virtual power with virtual forces, but that turns out not to be very useful in mechanics. It turns out to be useful if you think about hypothetical virtual velocities for the real. Okay. Now, what is this, the statement? So the virtual velocities of our system, so the virtual power of the applied forces in our system, that's easily written down. That is a delta P is a Fi delta dot Xi. And then I have to define, of course, what are my forces. And in our case, for our system, the Fi's are, it's like Fx1, Fy1, M1, Fx2, Fy2, and M2. And likewise, these coordinate speeds are x dot 1, y dot 1, phi dot 1, x dot 2, y dot 2, phi dot 2. And if you want virtual, then you just put a virtual everywhere, whatever. Okay, now I have defined everything. That is the virtual power of our system, right? Because I take all these coordinates and all these forces. Now the following statement, the system is in equilibrium. If the virtual power of these applied forces is 0 for all virtual velocities, delta dot xe, as long as they're not all 0. If they're all 0, then it's sort of stupid. Then the result is always 0. And this is what we're going to use because we want to know about equilibrium. There's one problem. It says something about equilibrium, and actually I'm not interested in equilibrium. I want to know motion, right? So how do we get motion into this? Because equilibrium is just statics, and that's, you passed the first year course on that, so that's not interesting. How are we going to do dynamics? There was somebody in the audience who had a nice way to make from every dynamics problem a statics problem. What did you use? You learned to write in. No. Yeah, exact. That's the word I'm looking for. D'Alembert forces. So, what is the trick? Well, D'Alembert forces is a trick to make from a static problem. I'm running ahead, from a dynamic problem, making a static problem. So you have a dynamic problem, and you cook it into a static problem. And how do you do that? Well, in statics, of course, you write sum of the forces is 0, right? And let's put an index there. That's how we solve our statics problems. You take bodies, you say sum of the forces is 0. But now we put some dynamics to it, so we add some dynamic forces, and the dynamic forces which we add are D'Alembert forces or inertia forces. And the inertia forces I define as a mass times acceleration. And let's keep it a bit vague for now. Just as mass times acceleration. Indexes will come later. And then, so let's drop the I here for now to learn the concept. So sum of the forces is 0. We're going to add inertia forces, and then we're going to write, well, so apparently the sum of the forces plus the inertia force must be 0. And that is totally equivalent with writing, of course, our Newtonian equation. The sum of the forces is mass times acceleration. Right? But now I cooked everything into a dynamics problem by introducing these applied inertia forces, and then now everything is static. So if I now take my definition of my virtual power, how does it go? Well, let's do it again. So virtual power now becomes delta P equals these. Well, now I have to be careful. I have my applied forces, but I also have my inertia forces times my virtual velocities. So that's now my first. And I have to define these things in a correct way, meaning my inertia forces I is some mass matrix, so Mij times x double dot j. And we put a minus sign in front of it. And I add it up. So if I now write it out, I say, oh yeah, delta P is apparently the applied forces minus the mass times the acceleration times delta x dot I. Well, and that should be 0 for all velocities which are not equal to 0. And then what can I do? Well, to find out what is the solution of this whole problem is you can take arbitrary velocities. So, for instance, you take x dot 1 is 1 and the rest is 0. If you put that virtual velocity in the equation, what is the result? Then I get the following equation: F1 equals m1j times x double dot j. And I mean, you can do that for x dot 2 is 1. And then if you continue like this, well, you already feel it coming, right? In the end, we get Fi minus Mij x double dot j is 0. Or we just get our Newton-Euler equations back. In general. So, okay, you say you start with Newton-Euler, then you define virtual power, and then you define what is equilibrium. You put in inertia, and then you get back to the Newton-Euler. That doesn't really help. But the trick is, of course, in these virtual velocities, because in this case, virtual velocities are apparently free. But is that the case in our system? Now we must raise the question. Again, I'm writing down my virtual power, which is my applied forces minus my inertia, and I drop out again. Yes, I see it. I see it. Yeah. I see. Yeah, I have to scan again. Oh, life is beautiful, right? So this was the 4th time? Yeah, okay. Oh yeah, on the other hand, we are getting very skilled in this now. Always stay on the bright side. Okay, so these are my expressions. Yeah, get back. So virtual velocities J. For all virtual velocities, well, they have to actually they have to fulfill the constraints. I mean, you cannot come up with arbitrary velocities in our system. You cannot say in the vertical position all the velocities are upward, because then you will pull the system apart. So there is apparently a restricted set of velocities. So all of which, yeah, I write fulfill the constraints. And remember, so we have to put, as I always say, that is our glue. We have to put our glue to the system in some way. And this glue also has to apply to our virtual velocities. Now, where do we get our glue from? Of course, our glue is just our constraint equation. So how many constraint equations? K constraint equations in xi is 0. These are our constraint equations. And now we have to find some way to make sure that these can follow these constraints. Well, first of all, the constraints are in the positions. So we have to make one step, we have to write them down in velocities. But that's easy. Just differentiate, right? So constraints on the velocities are constraints on velocities become, well, if you write that nicely out, you get dck differentiated with respect to xi times x dot I is 0, right? Okay. Again, we have a shorthand notation for that. I hate writing all these deltas and things. So we write it as C comma I, which implies this differentiation, this comma, this, and then times x dot I. Oh, that's not a nice x dot. X dot I is 0. And in our case, k is 1 to 4, right, and I is 1 to 6. We have 4 constraints and we have 6 coordinates. So these are these differentiations, the ones and the zeros and the cosines and the sines in our expressions. Now this is about real velocities. So what are the constraints on the virtual velocities? So constraints on the virtual velocities. Well, hopefully you got the message from the start of the lecture. You just copy the whole thing, right? And on purpose I will use copy and paste. So we copy the thing, we write it here, and the only thing we add is this magical symbol. Well, those are the constraints on the virtual velocities. I mean, virtual velocity is just some set of velocities. So now we know, okay, we have our virtual power, we have our constraints on these velocities. So now we can rewrite the whole thing. And we say virtual power, which is this Fi minus Mij x double dot j times virtual velocity j should be 0 for all virtual velocities, j, where we say, well, c k comma j delta x dot j is 0. So now these virtual velocities have to fulfill these constraints. Now, if we look in detail, these are like 4 by 6. This is this ckj, and then here we have these delta x dot j, which are 6 equations, is 0. So we have 4 equations and 6 unknowns. Can we solve that? No. I'm not going to sing. It's the Cole Porter problem, and it's anything goes, but I'm not going to sing this time. So what we could do is we could say, well, if there are 6 freedom, that's number 5, right? Oh, it's still there. Still there. Yeah, you're still there. You. So what we could do, it really destroys the flow of the lecture, right? Oh, anyway. So what we could do based on these, these 4 equations and these 6 unknowns, we could write everything. If you have 4 constraints on 6 variables, you could say, well, there are 2 degrees of freedom. So we can write everything in two variables. And then you have to pick 2 of these. And you could say, well, I take x1 and y1 of body 1, or I take x1 and of body 1 and x2 of body 2, or I take y1 and x2 or phi1 and x1. And I mean, out of these 6, you can make a whole number of combinations of 2 variables. And so the choice is a bit arbitrary which you take. And one thing we don't like in mechanics is arbitrariness. We don't like it. We don't want it. So we're not going to do that. I mean, a smart mouse would think, oh, use those 2 angles. They describe the system well. Yeah, okay, smart mouse. But we're not all smart mouses. Mice, sorry. So what do we do? Well, there is again a trick, and the trick is called, is made up by, unfortunately not Euler, it was Lagrange. And we're going to use Lagrange multipliers. And it's really magic. So what you do is you try to incorporate your equation, your constraints by means of Lagrange multipliers, and lambda k as many as we have constraints. So what am I going to do is I'm going to make a new virtual power expression. I'm going to take applied forces, inertia forces, virtual velocities, j, but now I'm going to add a term, and I'm going to add lambda k ck j delta x dot j is 0. And now I say this can be 0 for arbitrary velocities. And why can it now be for arbitrary? Because I put that condition on the 0 into the equation. And you could read like these Lagrange multipliers are like penalties, or there are various ways to look at it. But I make it part of the equation. And the moment this is not 0, it's penalized by this lambda k. Yeah? That's the whole idea. Now if I look at my system, if it's now for arbitrary ones of these, then I can take it for 1, 0, 0, 0, 0, 1, 0, 0, so it's apparently for every j. So I get j equations. So I get j equations, and these are actually our equations of motion, of course. Fi minus mij x double dot j plus lambda k ckj is 0. Now you may have noticed that we have enlarged, of course, our variables. Initially we had here our 6 unknown accelerations, but now we suddenly have our 4 lambdas, so these are our unknowns. Meaning we have a total of 10, and the number of equations is 6, so we cannot solve that. We need equations. Which equations do we need? We need our glue, right? So we need to add our constraints, and on the level of our variables, and our variables are accelerations, so coming from ck x j is 0, we go to ck j x dot j is 0 to, it's just differentiation, ck j x double dot j plus ck l m x dot l x dot m is 0. So we need to add this guy. So if you have this guy, 6 equations, we have 4 equations here, and then in total we have 10 equations, and we have our 10 unknowns. So this set we now can nicely write in some sort of strange mixed matrix vector notation. Well, the variables are x double dot j, and of course lambda k, our multipliers. Here we have our mass matrix, mij, and then reading at the equation, here we have our ckj, and it is with a minus sign apparently, minus ckj. Yeah. And then on the right hand side, we have our applied forces. Those are my equations of motion. And then here, what do I write? Well, these equations. So this is ckj. And here we all have zeros, right? There's nothing to do with these, apparently. And then on the right hand side, I have minus k lm x dot l x dot m. And this is what we call our set of differential and algebraic equations. And we usually put it around. Okay, algebraic and differential equations. Come on, also. Also. And our algebraic equation is this, our differential equations are that, so, and we call it our DAEs. And of course they comply very well with what we previously saw, that we have a matrix here, we have A, we have B here, we have zeros, here we have the x double dot, here we have the constraint forces, and here on the right hand side we have the applied forces and some terms. So we clearly see this relation, right? Like A is minus BT or something like that, or plus BT. But note that the only thing we used here are constraints. No, without the use of free body diagrams, I have constrained forces. Because if we used here constrained forces and here we use lambda k, they have to be constrained forces, these multipliers. These guys. And we can also reason back that they should be forces, because this is our equation of motion, right? And how do we get that? From our virtual power. Virtual power we understand. So here we had power equation. Now this was forces, and this is velocity. This is velocity, so this must be forces. This is a Jacobian. A Jacobian is just with units and 1 and with a cosine, so there's no dimension to it. So these must be forces. There's no other way. See you all next week.